I was watching a patient in the rehabilitation clinic last week. For 20 days, he'd been staring at his own feet, his knuckles white as he gripped the parallel bars. To anyone watching, it looked like a simple, physical struggle muscles versus gravity. He kept telling me he was waiting to feel steady before he took a step. He was waiting, he thought, for his brain to receive the signal from his legs that the floor was solid and he was safe. But that's not what was actually happening. His brain wasn't waiting for reality. It was hallucinating a catastrophe. Behind his eyes, his neural networks were running millions of microsimulations, and every single one of them ended with him face down on the linoleum. He wasn't seeing the floor as it was. He was seeing his own prediction of failure. Then something shifted. The room went quiet. He stopped trying to see the floor and just stood. For a fleeting second, the predictive noise stopped. The machine in his head paused its frantic guessing game, and for the first time in a month, he actually encountered the room. We've always been taught that our eyes are like cameras and our brains are like recorders, documenting the world as it unfolds. We assume that reality arrives and we simply witness it. But modern neuroscience is beginning to whisper a much stranger truth. Your brain doesn't actually see the world, it predicts it. At this very moment, your mind is not passively receiving the light from your screen or the sound in your room. It is actively constructing a model of what it expects to find there, and it only bothers to check the outside world when those expectations fail. Most of what you call reality is actually a controlled hallucination, a high-stakes guessing game where your brain is the scientist, the hypothesis, and the laboratory all at once. Once you realize that your brain prefers a familiar lie to an expensive truth, your entire sense of self begins to look very different.
What's fascinating here is the sheer magnitude of the paradigm shift this represents for our fundamental understanding of human perception, I mean.
Yeah, it's a complete inversion of what we're usually taught.
Exactly, because for centuries, the prevailing model of the mind was heavily, almost exclusively, bottom-up. Information was thought to strike the sensory organs, travel up the nervous system in this linear sequence, and eventually assemble into a conscious experience. But this deep dive we are undertaking today entirely inverts that classical model.
Right, because predictive processing reveals that the brain actively constructs perception through anticipation and highly calibrated error correction.
Precisely. Everything you are experiencing right now, the acoustic properties of this voice, the spatial dimensions of the room you're in, it's an active top-down neurological projection. You are not experiencing a bottom-up recording. You're experiencing your brain's most highly optimized guess about what is causing the sensory perturbations at your nerve endings.
Okay, because to truly grasp the mechanics of the predictive brain, we really have to view the brain fundamentally as an inference machine. And while the neuroscience mapping this out is cutting edge, the foundational idea is actually not totally new.
No, it has a rich history.
Yeah, if we look back to the mid-20th century, there was the cyberneticist, W. Ross Ashby. He proposed that the entire function of the brain, at its core, could be summed up in a single directive error correction.
Right, Ashby suggested the brain is essentially a system-seeking equilibrium, and it does that by constantly identifying and correcting deviations from its expected state.
And we can trace the lineage even further back, right, to Helmholtz.
Absolutely. Hermann von Helmholtz in 1860. He was a physicist and a physician, and he first depicted perception not as a passive reception of data, but as probabilistic knowledge-driven inference. Helmholtz grasped this fundamental physical truth about human biology. The brain is locked inside a dark, silent skull.
It's completely sealed off.
Exactly. It has absolutely no direct access to the outside world. It cannot reach out and touch a tree. It only has access to ambiguous, highly compressed electrical impulses from the sensory nerves.
I mean, the brain is essentially sitting in a pitch-black vault. It's like a telegraph operator sealed in a windowless room, just receiving millions of Morse code taps every second. And the operator has never seen the outside world, yet they have to deduce whether those taps mean there is a dog barking or a car approaching. The only way to make sense of that meaningless electrical noise is to infer the hidden causes based on past experience.
Right. The operator cannot just wait for a complete picture to be transmitted. The data arrives too slowly for real-time survival. They must anticipate the message. And today, this century-old insight has evolved into the rigorous framework of hierarchical predictive coding. To understand how the brain mathematically manages this, we can look at a relatable technological parallel.
Digital data compression, like video streaming or JPEGs.
Exactly. When you stream a high-definition movie, The server isn't actually sending you millions of fully rendered independent photographs. Transmitting every single pixel of every frame over a network is massive.
Right. It would require an impossible amount of bandwidth. The stream would constantly stall.
Instead, the algorithms are designed with an underlying predictive model. The system predicts what the next frame will look like based on the current one, because most of a video is static. The background wall, a person's face, it only transmits the errors.
The differences, yes.
It only sends the data for the specific pixels that changed in a way it didn't anticipate, like the sudden movement of a hand. This predictive architecture saves enormous amounts of bandwidth.
And this brings us directly back to human neurobiology. The human brain operates with the exact same metabolic economy, doesn't it?
It has to. Generating and processing neural signals across billions of synapses is biologically expensive. It consumes vast amounts of energy. From an evolutionary standpoint, the brain cannot afford to act like an uncompressed video camera.
It can't constantly transmit every redundant detail, the color of the wall, the hum of the refrigerator, all the way up to the higher cortex.
The metabolic cost would be completely unsustainable. Instead, the brain predicts the environment. It generates a top-down model and only transmits the unpredicted changes upward. And the neurobiological architecture making this possible is breathtaking. The cortex utilizes what is known as a duplex architecture.
Let's break down that duplex architecture because the physical wiring is essential here. We are talking about the cortical columns, the vertical pillars of neurons that form the basic processing units of the cortex.
Right. And within these columns, there are functionally distinct subpopulations of cells. First, there are the representation units,
which are typically the deep layer pyramidal cells, right?
These deep layer neurons carry the brain's internal model. They encode your beliefs, your memories, your expectations. Their primary function is to send predictions downward, moving from higher abstract areas down to lower sensory-specific areas.
So the deep layer cells are broadcasting the hallucination, the prediction of what is about to happen.
Yes, generating the expected sensory state. Then you have the counterpart, the area units. These are the superficial layer pyramidal cells closer to the surface of the cortex. Their dedicated job is computation.
They compare the downward prediction against the actual incoming sensory data.
Exactly. When there is a discrepancy, when reality does not match the hallucination, these superficial cells compute that difference and pass that specific prediction error upward to the next level of the hierarchy.
This completely reframes how we think about the flow of information. We usually imagine the eyes acting as windows, sending a full, high-resolution picture up into the brain. But in this model, the forward connections don't carry a picture of the world at all. They only carry the residual errors.
The specific fragments of input that the internal model failed to predict. And the backward connections carry the rich, detailed predictions, attempting to silence or explain away the incoming errors. If the prediction perfectly matches the sensory input, the error units remain completely quiet.
No signal travels upward.
You perceive the world seamlessly, but the actual data processing is minimal. If we connect this to the bigger picture, this specific duplex architecture is the physical implementation of a broader, unifying theory known as free energy minimization, the cornerstone of the Bayesian brain hypothesis.
Okay, free energy minimization sounds like a concept borrowed from a thermodynamics laboratory. How does this physical principle map onto the brain?
In information theory, free energy is essentially a measure of the difference between an organism's internal model and the external environment. For any self-organizing biological system, the overarching imperative is to minimize this free energy. Mathematically, that equates to minimizing surprisal.
Surprisal being a formal measure of uncertainty or prediction error.
Exactly. Biological systems cannot survive long in states of high surprise. If a fish is constantly surprised by the temperature of the water, it perishes. By continuously updating its internal models to better predict sensory input, the organism ensures its internal states align with external reality. It avoids the fatal surprise of an unpredictable environment.
Let's ground this complex mechanism with some concrete examples to illustrate how this plays out in your daily life. Consider the visual cortex hierarchy. Imagine you are walking down a familiar street and you expect to see a specific house on the corner. That high-level expectation actively engages a specific region in your brain called the parahippocampal place area, or the PPA.
Right, the PPA specializes in recognizing spaces and architecture. It acts as a high-level generative node. Because you are on a familiar street, The PPA generates a strong prior belief about what should be on that corner, sending top-down signals to prime the lower visual areas before your eyes even focus on the structure.
It's practically issuing instructions. It tells visual area V2 to expect specific corners and roof lines, and it sends signals all the way down to V1, the primary visual cortex, to expect specific vertical and horizontal lines.
And when you finally look at the corner, if the physical house perfectly matches that detailed internal prediction, the incoming light data simply confirms the expectation. The superficial error units in V1 and V2 remain quiet. The signal is canceled out. You perceive the house, but your brain expended minimal effort to see it.
Because it had already constructed it internally, you are essentially seeing your own memory of the house, validated by a quick sensory check. We can see this in language too, like sentence completion. If you read the phrase, because you are a fluent speaker of English, you already know what word comes at the end of this, your brain automatically generates the word sentence.
Yes. The prediction is so strong, based on linguistic statistical learning, that the brain effectively hallucinates the auditory and visual signature of the word before your eyes even scan the text.
But the true mechanics of the system are revealed when the prediction fails. Imagine a third scenario. You're walking down that familiar street. Your PPA is projecting the standard house prediction. But overnight, someone demolished the house and replaced it with a Futuro house, one of those bizarre UFO-shaped plastic structures from the 60s.
Now you have a problem. Your brain is pushing down an expectation of square corners, but the raw sensory light data hitting your retina is entirely contradictory. You're seeing a giant smooth ellipse and metallic surfaces.
The superficial error units in V1 and V2 are suddenly flooded with data that cannot be explained away. Massive prediction errors are generated, surging up the cortical hierarchy, demanding an explanation.
The brain tries to find an intermediate model, a strange tent, a parade balloon, but the data doesn't fit. This unresolved error triggers an immediate alert and orient response. You physically stop walking. You stare. Your conscious attention is entirely hijacked.
The brain is furiously forced to revise its internal model, carving new neural pathways so that if you ever see this Futuro house again, the surprisal will be vastly reduced.
And that phenomenon transitions us directly into the mechanics of attention. We must understand how the brain determines which prediction errors are worth processing, because the environment is incredibly noisy.
Right. If the goal is to minimize error, why doesn't it constantly update its model for every single anomaly? Light fluctuates, acoustics bounce, and our sensory organs themselves have inherent biological noise.
If the brain attempted to update its global model for every microscopic error, it would collapse under computational overload. It must continuously balance prior expectations against the reliability of new evidence. It decides whether a discrepancy is meaningful or just static through a mechanism called precision weighting.
Precision weighting is the brain's filtering system. It's essentially the brain's measure of confidence in a particular signal.
Correct. The brain dynamically alters the gain, or the volume, on specific error units. This volume control is heavily mediated by neuromodulators, primarily dopamine and serotonin, alongside acetylcholine. If a signal is highly reliable and carries critical information, it turns the volume up.
The neuromodulators increase the synaptic gain. The error is amplified into a loud, undeniable signal that forces its way up the hierarchy. And this is what we subjectively experience as paying attention.
Exactly. Conversely, if the signal is deemed noisy or irrelevant, like the hum of an air conditioner, the volume is turned down. The superficial error units are dampened, and the top-down prediction remains dominant. Attention is not a spotlight illuminating the outside world. It is simply the brain internally increasing the precision of specific sensory prediction errors over others.
So what does this all mean for our motivation to interact with the world? If the brain just wants to minimize surprise, why do we ever leave our comfort zones? This brings us to curiosity and learning. Within this framework, prediction errors are the fundamental biological drivers of human exploration.
This is where the model expands from perception to action. We can examine this through the prediction appraisal curiosity exploration framework, the PACE framework.
When you encounter a situation that doesn't make sense or hear a claim that feels intuitively off, you experience confusion or mild anxiety. That uncomfortable feeling is the subjective manifestation of a prediction error.
That initial failure is the prediction and appraisal phase. The sudden influx of unpredicted data plunges the cognitive system into disequilibrium. Operating with a faulty model is highly dangerous from an evolutionary perspective.
Therefore, curiosity, the C in the PACE framework, is a powerful, biologically driven motivation to resolve that uncertainty. You are compelled to explore. You are driven to gather more data and radically revise your internal model until equilibrium is restored.
And this maps onto the advanced mathematical formulation of curiosity known as active inference. The predictive brain does not sit passively. Organisms physically act upon the world. We actively fulfill our predictions and deliberately seek out data that will resolve internal uncertainties.
We interrogate the environment.
The brain calculates what is mathematically known as epistemic value within Bayesian experimental design. It attempts to determine which physical action will yield the maximum expected information gain.
Curiosity is the brain constantly asking, which movement, which shift of my gaze will return the precise sensory data required to resolve the highest amount of uncertainty? We actively design behavioral experiments to test our hypotheses against reality.
Wow.
In other words, perception is not passive. It is an active construction. The brain is constantly asking, what do I expect to see? Then it compares that expectation with incoming signals from the senses. When the prediction is correct, the brain barely needs to adjust anything at all. When the prediction is wrong, the brain updates the model. This process is known as predictive processing, and many neuroscientists now believe it may be one of the fundamental principles of how the brain works. In this view, the brain is less like a camera and more like a scientist, always forming hypotheses about reality and then testing them. But this insight leads to a deeper philosophical question. If the brain is constantly predicting the world, then perception is not simply the world entering us. It is a dialogue between expectation and experience. Reality, as we encounter it, is partly shaped by the mind that observes it. This does not mean the world is imaginary. The world is real. But what we experience is filtered through prediction, interpretation, and meaning. In that sense, the observer is never fully separate from the observed. Science, slowly and carefully, is rediscovering something philosophers have long suspected. The mind is not merely inside reality. It participates in it. Perhaps the greatest mystery is not the universe itself. The greatest mystery may be the mind that is able to notice it.
This raises an important question regarding epistemology and our very definition of existence. If perception is a controlled hallucination shaped by prior models, where does the mind end and the physical world begin? To navigate this blurring of boundaries, modern physics and computational neuroscience utilize the mathematical concept of the Markov blanket.
The Markov blanket sounds dense, but it's vital. How do we define this boundary without falling into solipsism, the idea that only the mind exists?
A Markov blanket is a statistical boundary. Think of it as a holographic screen, or the membrane of a single cell. It cleanly separates the internal states of a system from the external causes in the environment. It defines the conditional independence of the organism.
But it's not an impenetrable wall. It's a membrane of exchange. The internal mind and the external physical world interact through two pathways, sensory inputs penetrating the blanket, and active states or motor outputs perturbing the environment outside it.
Therefore, existence is interaction. To be a conscious entity simply means possessing a Markov blanket that maintains internal structural integrity while exchanging information with the void beyond it. Through this lens, everyday objects, a house, a book, are not entirely objective entities sitting passively.
They are constructs. They're regimes of low entropy signals. Your brain generates the concept of a book to instantly minimize the prediction error of interacting with the visual shape, the tactile texture, the weight, and the patterns of text. The book is a highly efficient predictive hypothesis. To make this profound philosophical shift more concrete, we can examine altered states of consciousness. It demystifies experiences often viewed as mystical. Consider dreaming. When you go to sleep, your biological relationship with your environment fundamentally changes.
During sleep, your brain is almost entirely sequestered from external physical input. The sensory gates are largely closed. The sleeping brain chemically turns down the precision of sensory prediction errors to near absolute zero.
Because the bottom-up sensory input is no longer granted mathematical weight, the brain's massive generative model runs completely freely. It generates a continuous flow of top-down fantasies. This is why dreams can be so incredibly vivid and physically impossible, but it's a critical biological mechanism for housekeeping.
Without the demanding interference of waking sensory data flooding the air units, the brain minimizes the complexity of its models. It runs simulations to prune redundant synaptic connections, optimizing the generative architecture so it can process the waking world more efficiently the next day.
Now contrast dreaming with the neurochemical effects of psychedelics. Classic psychedelics like psilocybin act as agonists, binding to and activating the 5-HT2A serotonin receptors, densely concentrated in the deep layers of the cortex.
By binding to these specific receptors, psychedelics radically alter the brain's precision weighting mechanism. But differently than sleep, they chemically reduce the precision of deep, high-level prior beliefs. These are the rigid models that dictate your sense of identity and standard categorization of the world.
Simultaneously, while those high-level priors are weakened, the precision of bottom-up sensory input is enhanced. The normal filtering system is disabled. The rigid top-down models that compress reality into categories like table or self collapse. The raw, uncompressed sensory data floods upward.
The phenomenological result is ego dissolution. The constructed self model loses its structural integrity. Furthermore, there is a hyper-awareness of the sensorium. The world appears vibrantly intense and interconnected precisely because the brain's usual rigid predictive filtering has been chemically dismantled. The raw data of the world pours in.
There was a case study I read about a woman in London named Sarah who struggled with a severe form of anxiety that made every crowded street feel like a battlefield. Her brain's predictive engine was overtuned to threat. It saw a reaching hand as a weapon and a loud laugh as a scream. She participated in a pioneering clinical trial that used a combination of biofeedback and predictive coding therapy. Instead of just talking about her fears, she worked on reweighting her sensory inputs. She practiced standing in a park, consciously lowering the precision of her internal alarm system while leaning into the surprise of a peaceful environment. Slowly, she taught her brain that the lack of a threat wasn't a fluke, but the new baseline. She described it as retuning an old radio until the static of panic finally gave way to the clear signal at the present moment. I find Sarah's journey incredibly hopeful, especially for those of us navigating the high-stress digital landscape. It applies the cold logic of neuroscience to the very human struggle of mental health. Some might argue that this reprogramming approach is too clinical or mechanical, stripping away the soul's complexity, but I see it differently. If our suffering is caused by a prediction error that has become stuck, then understanding the mechanism gives us the agency to fix it. It's not about ignoring reality, it's about giving our brains the grace to update their models of the world so we can finally find a bit of peace.
Sarah's experience provides a remarkable window into neurocomputational psychiatry. Traditional psychiatry relies on symptom-based classifications. Computational psychiatry fundamentally reframes mental disorders.
It shifts the focus from the outward symptom to the underlying mathematical processing, viewing these conditions as specific mechanistic alterations in the inference machinery.
Exactly. We can detail psychiatric conditions as computational phenotypes. Take schizophrenia. The positive symptoms, auditory hallucinations, delusions, are characterized by aberrant precision weighting.
In schizophrenia, the balance is severely disrupted. The brain affords inappropriately high precision to its top-down priors relative to bottom-up sensory signals.
The brain leans too heavily on its own hypotheses. If the prior expectation of hearing a voice is weighted heavily enough by the neuromodulatory system, the generative model constructs that perception forcefully enough to completely override the silence of the external world. The delusion is the brain's logical attempt to minimize the massive error generated by this hallucination. This is strongly linked to NMDA receptor hypofunction.
Autism, intriguingly, often presents as the inverse. Autistic perception appears to stem from unusually weak prior expectations.
Yes. The brain chronically underweights its top-down priors and over-relies on immediate sensory evidence.
Because the top-down models aren't actively filtering data, the individual experiences reality completely uncompressed. The individual experiences an incredibly detailed but overwhelming flood of raw input, leading to sensory overload. The autistic brain struggles to compress the noisy world into neat regularities because every single detail is treated as a highly precise, unpredicted error.
Moving to mood disorders, depression can be described mathematically as a pathological attractor state. The depressed brain becomes trapped in a rigid predictive model defined by an inflexible negative prior belief about the self in the future.
Crucially, this exhibits blunted prediction error. The superficial units fail to signal adequately. Even when confronted with undeniable positive reality, the error signals are too weak to force an update. The positive data is ignored or explained away.
Finally, look at obsessive-compulsive disorder, or OCD. This is characterized by pathologically high precision placed on specific prediction errors. Regions like the orbitofrontal cortex and anterior cingulate cortex act as hyperactive error signals.
They are constantly falsely flagging that something is wrong. The compulsive behavior is a mechanism of active inference, a physical action driven solely to silence the immense false anxiety generated by a broken, hyper-precise error signal.
Correct.
Here's where it gets really interesting regarding the future of psychiatric treatment. By understanding the computational deficit, we can design better interventions. Take behavioral activation for depression.
When a patient is locked in that rigid attractor state, traditional cognitive restructuring sometimes fails because blunted prediction errors prevent the model from updating. Behavioral activation forces the patient to physically sample environments likely to generate robust positive prediction errors.
By deliberately exposing the sensory apparatus to high-contrast positive data, it eventually forces an active inference loop. The sheer volume overwhelms the blunted signaling, forcing the system out of the depressive state to begin updating.
We can also view pharmacological interventions through this lens. Antipsychotics act as dopamine antagonists. They tune the gain control on superficial error units, lowering the pathological volume of internal priors so external reality can penetrate the model.
Even more revolutionary is the use of ketamine for treatment-resistant depression. It acts on the glutamate system, rapidly improving depression by chemically enhancing sensitivity to prediction errors. It opens an intense window of neuroplasticity where the pathological state is broken down, allowing the depressed brain to be actively rewritten by positive evidence.
If we synthesize this entire journey, we have traversed an extraordinary landscape. We began with a patient struggling to step in a rehabilitation clinic. We plunged into the mathematics of the Bayesian brain, understanding that our cortical columns are metabolically constrained data compression engines. We navigated the profound blurring of the observer and the observed, recognizing our reality as a delicate construct maintained by Markov blankets. Finally, we arrived at a deeply mechanistic understanding of human suffering, viewing psychiatric disorders not as moral failings, but as predictive engines struggling with miscalibrated precision. Your reality is an active, ongoing masterpiece. It is a mathematically precise dialogue between the intricate generative models held within your skull and the chaotic void of the outer world.
Which brings us to a final, inescapable paradox regarding the biological architecture of our minds, a paradox often referred to in computational neuroscience as the dark room problem. If the brain's ultimate driving biological goal was simply to minimize surprise, reduce uncertainty, and drive prediction error to absolute zero, the most logical and metabolically efficient biological strategy would be straightforward. Find a completely dark, perfectly silent room, crawl inside, and stay there forever. A dark, silent room is perfectly, flawlessly predictable. There are no unexpected sensory inputs, there are no massive visual or auditory prediction errors to resolve, and the free energy of the system drops to its absolute minimum state. Yet, human beings do not seek out the dark room. We are relentlessly driven toward complexity, novelty, and difficult challenges. The reason we don't seek the dark room is because evolution encoded a deeper, overriding prior into the very foundation of our generative models we expect to explore. We are biologically mandated to seek out the unknown, to venture into highly dynamic, unpredictable environments, and to actively gather the very uncertainties we spend our entire lives trying to resolve.